Hello guys, welcome to Irodov problem solving series. But this time along with the problem solving, we will also try to understand how a variable mass system and rocket propulsion problems are solved and what is the concept behind its working. So we will be trying to understand it using the problem. So let's get started. So we are dealing with the problem number 1.178 and we are trying to understand variable mass system and rocket propulsion problems. So the problem is stating a rocket ejects a steady jet whose velocity is equal to u relative to the rocket. The gas discharge rate equals mu kg per second. Demonstrate that the rocket motion equation in this case takes the form ma equals f minus mu u, where m is the mass of the rocket at a given moment, a is its acceleration, and capital F is the external force. So this is the information which is imparted in the problem, and we are here to deduce the expression. So we are doing a prove that kind of a problem, but what is important for us to understand is that the same problem can be asked in MCQ format. So we need to understand and remember the standard results which we obtain. So let us begin the problem by first of all drawing the diagrammatic situation of the problem. So this is the scenario which we have. This is the situation of the rocket at t equals t, that is at a certain instant of time, and after a small time interval when the gas is ejected, the system takes the form v plus dv with the gas being ejected in the backward direction, which will generate a thrust force. So over here, the first thing that we can write is that at a time t, the mass of rocket is m, which is moving with a velocity v, and since the gas discharge rate is equal to mu kg per second, so mu kg per second is the gas discharge rate, so therefore we can say that mass dm is equal to mu dt. So in a small time interval, the mass which is ejected is equal to mu dt. So over here, this is the initial configuration of the rocket when it is having a mass m and it is moving with a velocity v, and this is the final configuration of the rocket where it has ejected a mass dm in the form of the burned gases, and its mass changes to m minus dm, and the velocity of the rocket becomes v plus dv. Now the next point which we have in the problem is that the gas discharge rate is mu, and the next thing which the problem is stating is that the rocket ejects a steady jet whose velocity is equal to u relative to the rocket. So we can say that the velocity of the gas ejected with respect to the rocket is given to us as u. So we can say that velocity of the gas minus velocity of the rocket is equal to u. Now since velocity of the rocket at a time interval t plus dt is v plus dv, so therefore we can say that the velocity of the gas v gas is equal to u plus v rocket, and v rocket in this scenario is v plus dv. So we can write it this way, that v gas is equal to u plus v plus dv. So we have the initial configuration of the problem and then we have the final configuration of the problem. So this is the initial situation and this is the final situation which we have. And now what we are looking for is we are trying to write the initial momentum, the final momentum, and then we will be writing the change in momentum associated with the rocket system, rocket and gas system. So if we write the initial momentum associated with this rocket or with this entire system, so we can say that the initial momentum associated with the system is equal to mass m, which is moving with a velocity v. So we have this one as equation number 1 that we have. Now the final momentum associated with this system, so the final momentum associated with this system, the mass of the rocket changes from m to m minus dm, where dm is equal to mu dt. So this is the final mass of the rocket and it is moving with a speed v plus dv. So this is the momentum associated with the rocket, and then we have momentum associated with the ejected gases. So ejected gas is of mass dm or mu dt, and the ejected gas is having velocity u plus v plus dv. So this is the final momentum of the system which we have, and we are marking this as equation number 2. Now over here, using these two equations, we can calculate the change in momentum. So the change in momentum dp of the system is equal to p final minus p initial. So if we subtract the final momentum and the initial momentum, then we will get the change in momentum associated with this entire system. So if we calculate this value, so we can say that the change in momentum dp is equal to p final. So p final can be written as mv plus mdv minus mu v dt minus mu dv dt plus mu u dt plus mu v dt, and then we again have the term plus mu dv dt. So this is the final momentum, and then we have minus mv. So this is how we write the final momentum minus initial momentum. So if we solve this expression, so we can say plus mv and minus mv cancelled out, minus mu dv dt and plus mu dv dt cancelled out, and then we can say minus mu v dt and plus mu v dt, this term also cancels out. So we are left with these two equations, m dv and mu u dt. So therefore we can say that the change in momentum dp is equal to m dv plus mu u dt. So this is the expression that we have, m dv plus mu u dt. So if we are calculating the force, so for calculating the force expression, we need to calculate dp by dt. So if we write differentiating with respect to time, so we are differentiating with respect to time. So on differentiating this term with respect to time, we get dp by dt, which is external force, which is equal to m dv by dt. This will give us the effect or acceleration ma, and then we also have mu u dt by dt. This is the thrust force which we have. So we can say that the equation is going to take the form dp by dt, which is external force F, it is equal to ma, and this one is mu u, which is thrust force. So therefore we can say that the effect ma can be written as the net result of F minus mu u. So we can say F is external force, mu u is thrust force, and ma is the net effect because of the net force. So over here, very interesting to understand the terms which we have evolved in this particular expression, what does these terms actually mean. So this was the expression which we were supposed to derive or deduce in the problem, and over here we are also mentioning that the terms which we have deduced over here, that capital F stands for external force, capital F stands for external force, mu u stands for the thrust force. So when we are writing capital F minus mu u, then we are writing net force. So this net force is equal to capital F minus mu u, and ma is giving us the effect of this net force. The acceleration is the effect of the net force, which is ma. So this is the first expression which we have deduced, and a very important one. This was problem number 1.178, and to solve the next set of problem which will be following this problem, we will be time again and again we will be using the same expression which we have obtained. So this expression becomes very important. So this was problem number 1.178.